This is section 1.7 of the text Precalculus by Ron Larson, 11th edition. Transformations of functions. Shifting graphs. Before we talk about shrinking and stretching, let's talk about the motivation behind transformations of functions. So we just finished section 1.6, which was about a library of parent functions. And all of those parent functions are so important because each parent function is responsible for an entire family of graphs. And it's called a graph family if it starts with the original parent function, say f of x is equal to x squared, and then we do some sort of transformation. So we shift it from side to side or up or down, or we flip it upside down, or maybe we expand it or contract it, and all of those are transformations that we're going to learn about. Now, as you can see, I have two functions graphed. I have the original parent function, y is equal to x squared, or f of x is equal to x squared. That's the one graphed in white. As you can see, I have a sort of teal blue color for the graph of f of x is equal to negative 1/2 x plus 3 quantity squared minus 2. Now, this actually is in the family of the parent function of f of x is equal to x squared. Each of the things that I have done to this graph are things that we're going to learn about today. So let's take a look, and we're going to, of course, learn these in detail, each one, but let's take a look at what happened. The negative accounts for flipping this upside down. The 1/2 accounts for the fact that this is wider than it was before. The vertex of my new graph is at -3, -2, and I can see that I have a minus -3 here, and I have a -2 here. So again, these are all things that we're going to learn about in detail in just a few moments, but this is our motivation behind learning about the transformation of functions. We're going to start by taking a look at vertical shifts. A vertical shift will shift our graph up or down. And we know that to shift something up or down, that must have something to do with the y values, because the y value is what tells us how far up or down from the origin that our new point might be. So that makes sense that we would add to the y value, or the f of x value of the original graph. So the way that we think about that is by adding or subtracting c. So as you can see in Desmos, I have y equals x squared plus c, and I have c set to 0. And if I start going towards the positive side, 1, 2, 3, and so forth, my graph isn't doing anything else except for shifting up and down. Now again, this is the parent function, but watch what happens when I go to the negatives. Now I'm shifting the graph down. So we can see that for a vertical shift, we're going to add or subtract a c value on the outside of the function. In the same way that we talked about vertical shifts, let's talk about horizontal shifts. We know that the variable responsible for how far to the left or right of the origin is x. So in order to shift horizontally, we're going to have to add or subtract a value from the x value of the original graph. Now what that means here to us is that instead of f of x is equal to x squared, it's going to be x plus or minus some value, quantity squared. So let's take a look. I have the same parent function that we had before, but notice I've now moved c to the inside. Now, when I added c when it was on the outside, that shifted the graph up. But when I add c, notice what's happening is it's actually going to the left. So I want you to remember, when we're talking about horizontal shifting, it's going to be different, the opposite direction than what you might think. And that's because the original function is actually x minus c, so we're subtracting a negative to move it to the right. So again, if I have a negative c value, then it's going to move that entire graph to the left. I do want to point out that with these shifts, that the graph itself remains unchanged. We're just shifting it around. Before we move on to other transformations, I want to practice shifting graphs. So we're going to use horizontal and or vertical shifts to match the graphs given using the new parent function of y is equal to x cubed. So we used y equals x squared for our practice, for our examples, and now we're going to use y equals x cubed for our practice. So that you understand what the parent function looks like, I have graphed it for you on the left. So now I want you to try to come up with the correct equations for each of the three graphs I have given you. Press pause, try all three questions, then press play to see how you did. So the first one, as you can see, is shifted up 4 units, and that's all that has happened. So I can see, because I've labeled the vertex, the original vertex is 0, 0, and now I have shifted the graph up 4. So if we're shifting up, we are going to be changing the y value, remember, so we're going to add 4 on the outside of the equation. So f of x is equal to x cubed plus 4. For the next one, again, the graph is simply shifted to the right, but keep in mind that when I'm shifting right or left, the sign is going to be the opposite way that I might think. So this should have an x minus 2 quantity cubed. So x minus 2, or again, we're shifting the x value 2 units. And the last one, all I really did was put together both the first practice and second practice. So I'm adding 4 to the outside, and I have minus 2 on the inside. So you have f of x is equal to the quantity of x minus 2 cubed plus 4. Reflecting graphs. We're going to begin by talking about reflections in the x-axis. So we know that the x-axis is the horizontal axis, and if we want to reflect something over the horizontal axis, we need the y values to change sign. So for instance, I have the point on my graph of 2, 4. Now, if I wanted to reflect that over the x-axis, I would need the y value to be different. I would need the y value to be at negative 4. And so watch what happens. Then if I'm changing the y value, I'm changing this to negative x squared, and you can see it does in fact go through that point 2, negative 4. Now I gave us a few others just so you can understand where the x values will go. Where the negative value will go. So here, if I'm looking for a negative or flipped over the x-axis, I'm imagining this portion of my graph to be now above the x-axis, and the legs, or the parts that go on to infinity, to be below. So notice here what will happen if I don't have this in parentheses and I just change this to negative. That's not what I expected to happen. Remember, we thought it should be reflected across the x, which means the negative has to be for the entire function. And so now we can see that we have reflected my original graph across the x-axis. And same for the last example. I have y is equal to x minus 4 quantity squared. I can just put a negative right here and it flips right over. If I were to have something on the outside, like say minus 3, I would have to make sure that all of that were in parentheses and I got the negative in order for it to flip over. Now we're going to reflect over the y-axis. And again, what we're looking for, just as we did on our last practice, is if I had the point, say 2, 4, as I did before, if I wanted it to reflect across the y-axis, I would simply need to negate the x value. Now, I want you to notice that that point is already on our graph because the parent function of y equals x squared is an even function. So if I were to make the x value negative, we can see that it's the exact same graph that I had before. And the same would go for our second example. if I were to make the x negative, it's not going to change anything because this is already an even function. So here's this with the negative, here's without the negative. It's the same because these are even functions. They're already symmetric to the y-axis. So I've got two more for us to look at. Here is the equation that we ended with when we were looking at reflections over the x-axis. So over the y-axis, this point down here, which is 4, -3, we want that to reflect across the y-axis, so we want it to be -4, -3. So that's where we want it to end up if it's crossing over the y-axis. So think about folding a piece of paper across that y-axis. So if I now replace x with -x, we can see that it does in fact flip across the y-axis. The same is going to be true for 2x minus 3 quantity squared plus 5. If I make that -2x, it's going to flip across the y-axis. Just as we did with slide transformations, let's practice with reflecting graphs. And so we're going to use reflections to match the graph with an equation, but I'm starting with the function y equals x minus 2 quantity cubed because that makes it much more clear as to which should be which. So if you would, press pause, try all three of these questions. Note that there's more than one correct answer for the last question. When you're ready, press play to see how you did. So for my first one, if you can see, the only thing that has happened is this portion has flipped downward and this portion has flipped upward. So it appears to be reflecting across the x-axis, and to reflect across the x-axis, we're going to have a negative y value. So notice the entire function is being multiplied by -1. Whereas comparing the original function to this function, I can see that the point 2, 0 has now flipped across the y-axis to be at -2, 0. So this is clearly a reflection across the y, and remember that means we're going to negate the x value. So the negative is going to go here. Now for the last one, I said there's more than one correct answer. This one, the easiest transformation doesn't have anything to do with reflecting. So you might have caught that I did in fact reflect it and then reflect it again. So I reflected both across the y and across the x. So I did two negatives. But the easiest transformation is simply a slide from here to the left 4 places. So instead of -2, it was +2 because that's a difference of 4. Non-rigid transformations. Up to this point, we have studied only rigid transformations, and those are transformations that keep the original shape of our figure intact. It simply moves it about our graph, our coordinate plane, or it flips it over, but the figure itself remains unchanged. So now we're going to look at non-rigid transformations, which are transformations that cause some sort of distortion. So you might see this called compressions or expansions or shrink or stretch or so on. So different textbooks call it different things, but really what's happening is the shape itself is going to be sort of expanded or blown up, or it's going to be pushed together. So let's take a look. I did include this summary for you, and I would encourage you to screenshot that or write that down, but we are going to talk about them just as we did with all of the other transformations we've learned. We're going to start by looking at the horizontal shrink or stretch. And remember that horizontal is left to right. And so it makes sense that from left to right that we would be changing the x value. Now, what's going to happen is we already know what happens when I have a negative on the outside, and that flips it upside down. And if I have a negative on the inside, because this is already an even function, nothing's going to happen. However, we're now going to multiply the x value by some constant value, And whether it's negative or not is not going to be the issue. Whether it's between 0 and 1 or greater than 1 is what the issue is going to be. So obviously, if I put a 1 there, that's the same thing as x squared. But if I put, say, a 0.4, now the original graph, just for reference, y equals x squared, is the one here in this horrible pinkish color. 0.4, as we can see, has stretched that graph outward. So it's like you're putting your hands on each side of this pink parabola and pulling outward with all your might to stretch that parabola. Whereas if I instead make a number that is greater than 1, it's like I'm taking my hands on each side of that pink parabola and squishing them together. So there's your workout for the day. Good work. Now, keep in mind that this is not the same thing as me putting a 4 on the outside. We're going to talk about that in a moment. So same thing here. If I want to take my original graph and I want to change it, I'm going to have to put that value inside the parentheses with x. So again, a number between 0 and 1, like 0.3. I can see that the graph remains where it was, but it has now expanded. And if I put 3, it is now compressed or shrunken. And lastly, if I have a situation like this and I put, say, a 5, now I do want you to notice this one's a little bit different. So the other two that I showed you, both were even functions. So they both had already a symmetry to the x-axis. And so no matter what I did, these these vertices didn't change. I can't seem to select that vertex, but you can see that, let's get rid of the white one for a moment. If I change this to 0.3, this value of 0, negative 2 is still the same as if I put 3. This is still 0, negative 2. However, I want you to take a look at this one. The vertex here, 4, negative 3. So I'm just going to put 4, negative 3 so we remember where that was. And now if I put a value like 7, see what happened to the vertex. It is now compressed as well. So that is an important distinction, that vertex can change because I've actually squished the vertex together along with the rest of the parabola. Now let's take a look at a vertical shrink or stretch. Just as we did before, for vertical, we're looking at the y-axis. So we're going to be changing the y value, which means just as we did when we were dealing with a negative, we have to change the entire function. So just as a reference, when we were changing this to be reflected, we had to put a negative on the entire function. So we need to be thinking about that when we're doing a vertical shrink or stretch as well. We're taking f of x times c, or y times c. Just as before, things will be different whether or not that c value is greater than 1 or between 0 and 1. So let's take a look just at our first example, which is just the parent function y equals x squared. Here, I can just put a number like 6, and obviously 6 is greater than 1. And this one's a little bit difficult because I want you to think of it not left to right, because right now it kind of looks like I took the sides of the parabola and squished it together from left to right. But what's actually happened is I've taken the sides of the parabola and I've pulled them upward. So I'm stretching it out, and that's why a number greater than 1 is going to look like I've sort of compressed it, but what I've actually done is I've stretched it. Same thing if I put, say, 0.6. So now it's like I'm taking my hand and pushing down on top of the parabola to make it a little bit fatter. Again, this is just for reference. Here was my original graph. Let's change the color of that. So there's the original parent function, and between 0 and 1, I'm now looking at me sort of pushing down on top of those and squishing it down just a little bit. Same thing for my next equation. So here's my original. And again, just as we did before, I need to make sure that it's going to be the entire function that is being multiplied by a value. So I'm not putting, say, just a 6 right here. I'm putting a 6 in front of the whole thing. Now, just as we did before, let's look, before I put the 6 there, the vertex was at 0, -2. But now that I put a 6 out front, that vertex is down here at 0, -12, which makes sense because now I'm taking that 6 and multiplying it by the x squared and by the -2 to make it -12. Same thing if I put a 0.6. So now that vertex has changed because, again, I'm changing the entire function. Last one, here's my original function. Again, don't be fooled by putting a number just right here. I have to have the entire function multiplied by some constant. So let's do a number between 0 and 1, which makes it, again, like I'm squishing down from the top, or make it 10, which means like I'm taking each side and stretching. I do have some practice for you on this one. Again, I'm using the shifted parent function y equals x minus 2 quantity cubed. Obviously, it's very difficult to determine what number I used, so I'm telling you the number will either be 5 or 1/5, so you can determine where do you believe I put those numbers. So press pause, try to write the equation of all 3 questions, and then press play to see how you did. So for my first one, we can see that the vertex is in the same place, which means the x value hasn't been shifted, so it has to be a y transformation, which means the entire thing is either multiplied by 5 or 1/5. Now, which one makes sense? Again, this seems to be gotten smaller, but really what we've done is we have stretched it, and so it should be 5, again, on the outside of that function, changing the entire function by multiplying by a value greater than 1. For my second example, as we can see, that vertex has shifted. It's now at 0.4, and that means that it has something to do with the x-axis. So that means it's going to be a number inside here next to the x. So is it 5 or is it 1/5? Well, what has happened using the x-axis is that, again, I've taken the sides and I've squished them together, so that also is going to be a 5. Now for our last example, as we can see, it is in the same place, so it's going to look like this one. But I can see that I have, instead of pulling up and stretching that, it's like I've put my hands on the top and bottom and squished it together. And so that's going to be a 1/5, but again on the outside of the original function. Coming up next, we're going to look at section 1.8, which is combinations of functions, composite functions.